Alright guys, so we're talking about the difference between linear and angular speed. We had the example of the ice skaters holding hands, doing a big circle. Ice skater on the outside of that circle needs to skate a lot faster to keep in line with the ones on the inside. That outside ice skater will have a very fast linear speed, even though the one towards the middle is not skating as fast. They will have a smaller or a smaller linear speed, but their angular speed, they're turning together at the same angle over time. So angular speed for either any of the ice skaters would be the same, but the linear speed is dependent on the radius, how far away from the center you are. Okay, so here's some of the formulas that we have. Remember that funny W is actually a lowercase omega, and that's angular speed. V is our velocity, so that's your linear speed. S is the arc length of the circle. R is radius. Thetas are in radians. Okay? So, yeah, you just gotta... Now, on the practice here, they even told you what formula to use. So if you're looking at this homework here, use the formula, omega equals theta over t, to find the value of the missing variable. Okay, well, I should be able to do this easy peasy. If I'm using this formula, right, and I know that omega is pi over 4 and it's equal to theta over t, all I have to do is solve for theta. What would you do? Oh, dopey. I know what t is. T is 5. Silly goose. So I just multiply both sides by 5 and I'll be done. 5 pi over 4. There's theta. Easy enough? Okay, and then I do the same thing for 10. Let's see. I have pi over 24 equals theta, which is 3 pi over 8 all over time. Huh. How am I going to solve this one? Sure, multiply both sides by t. Then I'll have pi over 24 times t equals 3 pi over 8. Now what? Yeah, why not multiply both sides by 24 over pi and get those out of the way? So, oh, sorry. Now, some things are going to cancel out for me. Pi will cancel with pi. 8 into 24 is 3 times. I get 9. Did you? Yeah. There we go. Oh, that'll do it.
I'm not getting nice numbers like 9.
Did you plug in the same spots?
No, I didn't. I think I'm just doing that.
Okay. So 14, they want us to use V equals R omega to find the missing variable. So let's see. I don't know what V is. R is 8. Omega 9 pi over 5. Well, I'm just going to multiply, right? That's it. And I'm in, what are my units here? But I'm in velocity, centimeters per second. And 16 here, same formula, V equals RW. V is 18, R is 3. I don't know what omega is, but now I do. It's just got to be 6. That's it. That's a funny. There we go.
Wait, can you go back to just moving number 14 and 26? Okay.
It's in your folder. All right. Then we had to do the back of the first page. Okay, so I'm trying to find angular velocity for the following. A line from the center to the edge of a CD revolving 300 times per minute. Okay? We ready? Everybody's ready? So, I'm looking for funny W. If I look at over here, well, let's see. Oh, here's one with funny W. Theta over time. Do I have... I have the time. Well, and I can turn that into theta. Right? I know 1 revolution is what? 2 pi. So if I do 300 revolutions, it's just 600 pi. So there's my theta. In what time length? Per minute. So, there we go. So I'm just going to use funny W equals theta over t to find funny W. Remember, I need this in radians, and you guys just told me 300 revolutions. In 1 revolution, I go 2 pi radians. So that's where 600 pi comes from. So I get 600 pi radians.
What's the official name for funny W?
It's lowercase omega.
Just lowercase omega.
Mhm.
There's not another word for that.
I guess omega, but I feel like you have to distinguish that it's lowercase though, because it's totally different than the uppercase one. Small omega?
Uppercase omega.
No, because omega or
Uppercase omega looks like that.
Oh yeah. That's Latin, right? It's Greek.
Greek. Yep.
You're the only one who
Okay, so per minute. So guys, they didn't specify what units I need to be in. So if I just leave 1, I'm in minutes. So this would be radian, 600 pi radians per minute. 600 pi radians per minute. Is this all right? Everybody's okay? Sure you do. All right. How about the second hand of a clock?
I didn't know how to
Now, notice they didn't give me anything about how long the second hand is, because it doesn't matter. Think about the second hand on the clock. Look at it. Look at that red second hand.
The second hand or the red seconds?
Seconds hand is what I mean.
Oh, that's
Guys, look at that red thing turning around. Okay? Imagine, are you listening? Imagine I went over to the clock and I just snapped the end of that red thing off, but it's still clicking at the same rate that it was before, right? Its angular speed is not going to change as long as the clock is functioning properly, right? Its angular speed will always be the same. The only time it's, right? No matter how long that red thing is. I could add several inches to that red thing. Doesn't matter. It's still going to turn at the same rate. That's angular speed. Well, imagine it was a nice one that actually kept going. That's one way to tell a real Rolex from a fake. A real Rolex, the second hand never stops. It's a continuous, right. It's a continuous flow. So, but anyway. So imagine that one was nice and they actually just kept moving. Right? So, do you guys get what I'm saying? It doesn't matter how long the second hand is. It's always going to do 1 revolution in a minute. Now, if you were, imagine I had a giant clock and it was like an amusement park ride. And you got to sit at the very end of that second hand as it spun around. You were like, whee! You're going to go so much faster. Haven't you ever been on a merry-go-round and the horses on the end go way faster than the horses on the inside?
It's been a while since I've been on that.
But you could imagine.
Merry-go-rounds are actually the most dangerous ride in amusement parks.
No,
Like, they
wrong.
nope.
Well,
have the most, like, rates of...
I don't know about any of that stuff.
Yeah, idiot 4-year-olds are the most, like, people who die the most in amusement parks.
All right, guys. Anyway, but you could imagine on the merry-go-round, the whole thing is turning at the same rate, but those horses on the edge have to go faster, right, to keep in line. So your linear velocity is going to be much faster on the outside than it is on the inside. Same reason, same thing with the ice skaters. All of these things that are turning like that, they all work the same way. Yeah.
Does this have any correlation to, say, if you're on a boat and you're in the front and the back, or like you're in the bus, you're in the back of the bus, in the front of the bus. Like when you go over a bump, the back of the bus goes higher.
To this, I don't know if there's a direct relation. Yeah, I'm not sure. But I know exactly what you mean. Like on a boat, and then you jump, and then if it's going down, you go way up.
Or about
Is that
like
what you
in
mean?
an elevator when it's blowing when you're a little kid, you just jump and you feel like you're free.
Oh, yeah. I don't think that's related to this particularly, but I'm sure there's lots of other physics things that it is related to. All right, so anyway, second hand of a clock, doesn't matter how long it is, it matters, because I know how fast it's turning. Isn't it going to do how many revolutions in a minute? One. And isn't one revolution is how many radians?
2 pi.
2 pi. So isn't it just the angular speed is 2 pi radians per minute? That's it. That's my answer.
That.
I mean, you can use the formula, right?
Yeah, the question is.
Well, it meant to come with this. Find W for the following, the second hand of a clock. So, W is, it's turning 2 pi radians in 1 minute. So that's its speed, 2 pi radians per minute. Angular speed, 2 pi radians per minute. If I ask you about the linear speed, I'd have to tell you how long the second hand was and where we are on the second hand. Are you at the tip? Are you halfway? I don't know. It would depend. Oh, speaking of which, look at number 30. Now I want to know, how fast are you actually traveling? If I put a little speedometer on you and you're here on the tip of a second hand of a clock that's 28 millimeters long. So imagine you're a little tiny, sure, you're a tic-tac on the second hand. And you're gonna, I was thinking like a fruit fly. And you could land on the second hand and go for a little ride. Whee! Right? So, any hoosers. Now I need to find V. Here's what I have. I've got a radius. Don't I know W for the second hand? I just found it. It's still a second hand. It doesn't matter if I'm talking about this clock, a clock downstairs, a clock in Hong Kong. As long as they are functioning properly and doing 1 revolution per minute. Isn't that weird? And it's weird that time is like a thing that we made up. Like hours in a day. Like why isn't it 30 hours in a day? It's all based off the sun, but you could have taken one period of time and broken it up. It doesn't have to be 24 hours. It could have been 100 hours. Could have been, yeah, it could have been whatever we wanted. Anyway, so I have R. I do have the angular speed. So let's see. I'm trying to find V. Let's see what I've got. Hey, I think I could use this one. Oh, wait, we did have another one that we didn't write down. V equals RW. There was another formula from our notes. V equals R times the angular speed. Let's use that one. V equals R times the angular speed. So the radius is 28 millimeters times the angular speed, which is 2 pi radians per minute. So that means I'm going to be going per 1 minute. 56 pi millimeters per minute. Okay. Is this making more sense or no? I especially think it's helpful to have all your formulas kind of somewhere in a central location that you can kind of look back on. They are. So,
Can you go back to that thing of the equation somewhere?
yes. There they, hold on. Let me put this sheet under. There you go. These are on your reference sheet. They're pretty much all here. Yeah, you've got angular speed, W equals theta over T. V equals S over T, V equals R theta over T, V equals R W. S equals R theta. Yep, looks like 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yep, they're all right here on the top right section of the back of your reference sheet.
Is it wrong to call lowercase theta W, or does it not matter?
I think it's wrong because it's not really a W at all, but it looks like a W to us.
Yeah.
I call it funny W. You call it whatever you like.
You says go.
Well, I don't know about that.
In this class.
Okay. Let's try 32, shall we? You guys. So, again, I'm looking for V. Find V for each of the following. A point on the tread of a tire, radius 18, rotating 35 times per minute. Okay. Well, I have this formula, V equals R times lowercase omega. I know the radius. I'm just going to have to figure out W, my angular velocity. Yeah, if it's rotating 35 times per minute, so 35 rotations in 1 minute, I can turn that into radians. 1 rotation is 2 pi radians. So it would simply be 70 pi radians per minute. Do we all agree?
You don't multiply V equals,
I'm just getting W.
oh, you're getting that.
Yeah, so that's 30 or 70 pi, but I just want everyone to see why. Right? 35 revolutions in a minute. Each one of them is 2 pi, so that would be 70 pi radians in a minute. Yeah? Always okay? So, then over here, 18, 70 pi. 18 times 70 is 1260. And this is centimeters per minute. All right. Yeah. Do you have a 60 under there? Then yeah. If they don't specify the units that they want, you can kind of do as you wish, but yeah. As long as you have 60 seconds, then yeah, you can do that. All right. So, we did not get to the next page yet. I'd like to try some of these together. They're a little bit tougher. All right, let's see if we can manage this. 33. A pulley has a radius of 15 centimeters. Suppose it takes 25 seconds for 75 centimeters of belt to go around the pulley. Find the linear speed of the belt in centimeters per second. Then find the angular speed of the pulley in radians per second. All right, so let's figure out what we need and what we have. So first part, I need to find the linear speed. So that's V. I don't know what V is. That's something I'm trying to find. I do know the radius. It's 15. I do have a time, 25 seconds. What do you suppose this 75 centimeters is?
It's the distance traveled over the known time.
So what letter would that be? Not the radius.
It
What?
would be P or S. P.
S.
One letter.
S. S is the length around, the distance around the edge of a circle. So if I'm going to pull 75 centimeters of belt, isn't 75 centimeters going to go around this pulley? Yes. Oh.
Wait, I thought you meant like fully round.
Well, I mean, that's what I'm trying to measure. 75 centimeters worth of belt is going to go around. So S will be 75 at the end of the day. Okay, so I have all these pieces. Let's see. I need to solve for V. Let's see if I have enough to solve for V. If I look back, hey, look, the very first one. V equals S over T. I have an S and I have a T. So S is 75, T is 25, which means that V is
3 centimeters per second.
yes, centimeters per second. 3 centimeters per second. So if you are going to zip 75 centimeters of belt in 25 seconds, it's going to move at a speed of 3 centimeters per second.
34.
Well, hold on. We got to do part B. Find the angular speed of the pulley. So how fast is that pulley turning? So angular speed, remember, is funny W. So now I'm looking for funny W, and I have all these other pieces. So if I look, let's see. I could do V equals RW, because I have V and I have R, right? So let's do that. V equals RW. V is 3. R is still 15. Divide by 15, divide by 15. I get 1/5. Remember what angular speed is in, radians per second. So I'm going 1 radian every 5 seconds.
How'd you get radiant?
It's always in radians per second. Angular speed.
What's the equation for W?
There's this one, that's theta over T. So radians per unit of time, whatever time you're in. But I use this one since I had the V and the R. And I just solve for omega. Okay, let's try 34. Let's see if we can figure this one out. 2 pulleys have radii of 20 centimeters and 6 centimeters respectively. The smaller pulley rotates 30 times in 12 seconds. Find the angular speed of each pulley in radians per second. So, can you imagine this?
Yeah.
Can you imagine there's a belt going around, or it looks like a bicycle chain, doesn't it? Like the gears on your bike. Same idea. You have a little gear and a bigger gear. Chain goes around it. The chain's going to move at the same speed, right? No matter where it is, no matter which... Oh, yeah, sorry. So the chain, if you're thinking about your bike, right, the chain is moving around these 2 pulleys at the same speed, no matter where you check it, right? If I tested the speed of the chain right here versus the speed of the chain right here, it doesn't matter. The speed of the chain is going to be the same.
Unless you go faster.
Right. Well, if I'm pedaling at the same rate, the speed of the chain is going to stay consistent. What's going to be different,
Yes.
No.
I have no idea.
Carpets.
They have belts.
Yeah, but that's not for the wheels.
I don't know enough about it.
Four belts. Four belts.
All right, guys. So what will be different here is how fast each of these gears spins, right? The smaller one's going to spin faster than the bigger one. So that's what they're asking us to find. What is the angular speed of each one? So let's start with the small, I don't know. Well, let's see, what do we have? I know the radius of the small one is 6. I'm looking for funny omega for the little one, so that's what I don't know. And I have a time, 12 seconds. And I also know that it rotates 30 times in 12 seconds. So what I'm going to have to do,
So it'd be 360 times.
I have to figure out theta. I have 30 rotations in 12 seconds. I need to change this into radians. In one rotation, what do? I'm going 2 pi radians. So now I can change this into radians per second. So let's do some fancy math here. And wouldn't that get me, it's a 1, that's a 6. Wouldn't it just be 5 pi? 5 pi radians per second. That's my W. Yep, radians per second. Sorry. So now I know W, 5 pi radians per second, but that's for the little one. So now let's see what I need for the big one. So, what is the same for the little and the big one? The speed, exactly. So I need to figure out what the linear speed is of the belt. So I can do that now for the little one. I know, but in order to find the angular speed of the big one, the consistency between them is the linear speed of the belt. So that's what ties them together. So once I know the linear speed of the belt, then I can find out how fast the big wheel's spinning. Because I don't know, for the big wheel, they didn't tell me how many times it rotates in that same 12 seconds. If they gave me that, then I'd pretty much be done. But I don't know how many times it's spinning around. So what joins these together is that belt. So I can figure out the speed of the belt, and then I can go from there. So let's talk about speed of the belt. So that would be a linear speed. Let's see, what could we use? How about our W, right? Because we have W now. So V equals RW. So the speed of the belt, the radius of the little guy is 6, and the rate at which the little belt is turning is 5 pi. So that means the speed of the belt is 30 pi. And we're in centimeters per second there. Which means that the big belt has that same linear speed. So as the belt is going around the big gear, it's going at that same speed. Right? Because the chain's going to move at the same speed no matter where you check it. So now that I know V for the big one, I can use the same one? V equals RW, and now I can solve for W for the big guy. Does that make sense? Yeah, are we all right? So, do we all agree that the linear speed of the chain's going to be the same everywhere? Right? And that's what connects these two gears to each other, is that belt, that chain, whatever.
So what's R for the big one?
20.
So it's 35, 20 equals 20 W.
Hold on. So my linear velocity is 30 pi. My new radius is 20, and I'm going to solve for W. What did you say it was?
30 pi equals 20 W.
Yes. So now I can just solve for the angular speed. So divide both sides by 20, and I get 3 pi over 2.
So this is basically just have formulas and can I have the 4 formulas on the front page? That's all right.
They're all on your reference sheet too.
Thank you.
Did you guys all take physics? This reminds me so much of physics. Just looking, okay, what variables do I have? Let me find an equation on my reference sheet that has what I have and what I'm looking for. Sometimes you have to use more than one equation that they bridge together. But there you have it. All right, so are we feeling confident enough to try 35? Oh, is that the last one? Ah, it's the last one. All right, so let's go for it.
Wait, just say before
Yeah.
you start it, I looked it up and apparently both types do use change.
Oh, now we know. Do you guys want to try 35 by yourself? Try it. Give 35 a shot on your own, and then I'll give you like 5 minutes or so. And we'll come back together and see if we all kind of figured out the same thing. I wonder if there's a way to pause the video. You would think, right? I could.
You could just put it together, cut it and post.
That's too much work for me. I don't know how to do that.